So we continue from where we left off. That is, we were in chapter 2. So we introduced the category of representations. We talked about intertwining operators, intertwiners, and we talked about irreducible representations and parliament of irreducible. I think we came up to the point of introducing the function space. We came to the point of introducing the function space, and we saw that the class function. I mean, we were introducing the class functions and such. Okay, so let me share my screen. Yeah, do this. Okay, where are we? Yeah. So suppose if everybody can see my screen,
Yes, yes.
if phi from G to GLV is a representation of G and the dimension of the representation is n, then each phi G can be thought of as an n cross n matrix whose entries are functions from G to C, right? It's just a n cross n matrix. Okay, the entries of course depend on G and the entries are complex numbers. I can think of V to be Cn as we have seen. We shall follow the treatment in Walter Lederman, which seems more direct. So we already taken the vector space to be Cn. The n squared entries of phi G are functions on G. They are elements of Lg, the vector space Lg. The character trace of phi, the character of the representation is trace of phi, is an element of Lg. But actually, it's a class function. So let us look at the definition. A class function. What is the class function again? Yes, a class function is basically, yes, please. A class function is a function from G to C which is constant on the conjugacy classes. And what is the dimension of the vector subspace of class function? It is basically the number of conjugacy classes, right? Because if I could take the conjugacy classes C1, C2, Ck, I could take Cj. I can take a function which is 1 on Cj, 0 elsewhere. That's obviously a class functions, and these will form a basis for the subspace, vector subspace of class functions. And this character, that is trace rho g. Trace rho g is denoted by chi sub rho. Chi sub rho. The character of the representation rho will be chi sub rho. That's a class function. Okay, so that's a class function. Now we are going to use the inner product on Lg. Lg is simply C cross C cross C. It is C to the power mod G. It is C to the power mod G. And we're going to use the inner product. And we shall be working with a unitary group representation. We have seen that every representation is equivalent to a unitary representation. So we are going to assume that we have a unitary group representation. So phi G inverse must be phi G star. In other words, what is phi G star? What is the ijth entry of phi G inverse? It is a jith entry of, you take the jith entry of phi G and you take the complex conjugate. There is it's a adjoint. Okay, Lederman does not work with unitary representations. He's he's working only with matrices over arbitrary fields, and especially he will restrict it to C, but he doesn't work with unitary group representations. And he uses fields which are co-prime to mod G. The use of unitary representations will be significant in the second half of the course and when we do compact Lie groups. So there is no point in giving up unitarity. So let Eij be an M cross N matrix, a rectangular matrix, mind you. M cross N matrix with 1 in the ijth position and 0 elsewhere. AB are square matrices of sizes M cross M and N cross N, so that AEJB is meaningful. What is the PQth entry of AEJB? The PQth entry of any matrix is EP transpose times a matrix times EQ. Remember that these unit vectors are column vectors. Of course, EP on the left hand side is a column vector in CM. So I taken the transpose here. and EQ on the right hand side is a column vector in Cn. Standard unit vectors. I'm going to use the same letter EP and EQ. That it should not cause any confusion. Okay. So what happens when I do the matrix multiplication? When I do the matrix multiplication, when I take EP transpose times A, I will get the P through of A. When I take B times EQ, I'm going to get the Qth column of B. So you see a transpose here. And then Eij has 1 in the ijth position and 0 elsewhere. So you can do the matrix multiplication and you simply get API BQJ. So this has been computed. So I have found the PQth entry of AEIJB. In other words, AEIJB will be API BJQ EPQ. The PQth entry is API BJQ, which means that the matrix is API BJQ EPQ. Okay, so this is 2.6 prime. And now, what about A star EIJB? When I do the star, I just have to switch the indices here and put a complex conjugate. With this simple preliminary out of the way, let us prove the basic lemma. The basic lemma is, let phi from G to GLMC and psi from G to GLNC be two unitary representations. And let us look at 2.7, the matrix given by 2.7. Phi G inverse Eij psi G. I'm fixing the INJ. I'm fixing the INJ and I'm summing over the elements of the group. Equation 2.7. This equation 2.7, the operator of course will depend on Ij. The matrix T will depend on Ij. I'm suppressing the dependence on Ij for now. That's an intertwining operator. Okay, let us check that it is intertwines. Phi of H applied to T. Phi of H applied to T is summation over G. What is the definition? What is the definition? Summation over G, phi of H, phi G inverse. So phi of H G inverse Eij phi G. Now what you do is that you introduce the H here also. You introduce the H here also. Okay, by making a change of variables. Put H G inverse equal to X, X inverse. So this will be phi X inverse Eij, and then this G will becomes XH. Because the G becomes XH and psi is a group homomorphism, the psi H goes on the right hand side. And you simply have this psi H is a common factor, summation over X, phi X inverse Eij psi X. Excuse me. Yeah. So that proves that T is a intertwiner because the left hand side factor is again T. Proof is complete. Now we have an intertwining operator, and now we have got two operators. We have got two group representations, phi and psi. Now we are going to make the assumption. Now we are going to bring in irreducibility, and we are going to think of Schur's lemma. Idea is to now use Schur's lemma. For this, we need to take phi and psi to be irreducible. So now, if phi and psi are irreducible, and if they are not equivalent, then the intertwiner must be 0, right? That's Schur's lemma. So every entry of T must be 0, which means that using 2.66 prime, 2.6 double prime and 2.7, we conclude that this particular thing, summation over G, summation over PQ, AIP G bar BJQ G, EPQ must be 0 for each choice of indices Ij. This must be true for this, every Tij must be 0 because phi and psi are not equivalent. So now the matrices EPQ are linearly independent. So every coefficient must be 0. So summation AIP bar BJQ must be 0 for all IPJQ. So that is one condition. On the other hand, if phi and psi are equal, and they are irreducible, again by Schur's theorem, the T must be a scalar. T must be lambda iji. Of course, remember T depends on ij, so lambda will also depend on ij. The scalar will also depend on ij. So T must be lambda ij capital I. Okay, and all, now if phi and psi are equal, they are both square matrices of the same size. So all indices ij, pq will run from 1 to n. So in place of 2.8 prime, we will get AIP bar G BJQG must be lambda ij delta PQ, right? Because it is a scalar, lambda ij times I capitalized delta PQ. Okay, and A and B must be equal. The matrices A and B are equal because the phi and psi are equal. So this reads summation over G AIP bar G AJQG equal to lambda ij delta PQ. Note that both equations 2.8 prime and 2.8 triple prime are inner product equations, right? You're summing over G, remember? It's an inner product on the function space. It's an inner product on the function space LG. And so it is basically an orthogonality relation that we have obtained here. And so let us summarize these observations as a theorem. Theorem 2.6, let G be a finite group. Phi and psi are irreducible representations of degree m and n respectively. And phi G is the matrix phi Pig. Psi G has been written as a matrix psi JQG. Okay, if phi and psi are inequivalent, then then these entries phi Pi and psi JQ are orthogonal with respect to the inner product, the Hermitian product that we have. If phi and psi are equal, in which case the degrees are the same, then the function phi IPG are orthogonal and form a linearly independent system for LG. Orthogonal means in fact none of them are zero. None of them are the zero functions, and that's what it means. Orthogonal and linearly independent. They're orthogonal and they're linearly independent. So I can normalize them, and I can get a orthonormal basis for LG. Only the last part needs to be verified, that they form a basis. Specifically, we need to compute lambda ij. The first part is easy. First part we already proved. So T is lambda ij capital I. So now take the trace of both sides. Take the trace of both sides. What happens? Lambda ijn will be summation over G trace. What is this? Trace phi G inverse Eij phi G. Remember that's exactly what we got here. We got the T, no? We got the expression for T, the intertwiner. This was the intertwiner, remember? Yeah, this one. We have to take a trace of this business. And now remember that the trace AB equal to trace BA. When you have two matrices, trace AB equal to trace BA. So I can commute because I'm talking to take the trace. So phi G inverse phi G will be identity. You can simply get trace Eij, and trace Eij will be simply mod G times delta Ij, because you're summing over G. Because trace Eij will be 0 if I is not equal to J. If I is equal to J, it will be 1, and you're summing over G. And it's going to be 1, 1, 1, 1 mod G times. So lambda Ij will be mod G by n delta Ij. Okay. So we have computed the lambda, and we got that they are orthogonal. And if I take a specific one and I take its inner product with itself, I get a non-zero number. This is clear? So the Hermitian product on LG will be taken to be 1 upon G. I'm going to average. I'm not going to take the standard Hermitian product. I'm going to take the standard Hermitian product and I'm going to divide by the number of the dimension of the vector space. Remember, our vector space LG is mod G dimensional. So now we see that if phi from G to GLNC is an irreducible representation, So if you take, the basic result is, if you have an irreducible representation and you take the matrices phi g, you take the matrices phi g, and the entries of the matrix give you an orthonormal system after a certain normalization. After multiplying the root n, you get an orthonormal basis for LG. It's going to be an it's going to be an orthonormal linearly independent system for LG. And how many are there? They are n squared, not n squared. Sorry, it is as many as the part. I mean, it is k. It is yeah, it is n squared. It's an orthonormal linearly independent set for LG. If we take a parliament of irreducible representations on G, if we take a parliament of irreducible representations, then this set is finite. If the degrees of representations are d1, d2, dk are arranged in increasing order, okay, then what is the story? It will be k less than or equal to d1 squared plus d2 squared plus dk squared less than or equal to mod G. So let Mj be the matrix of the jth member. So you got a parliament of irreducibles, and you got the jth member of the, and let Sj be the entries of the matrix Mj. Now Sj and Sl are orthogonal. Yes, any questions, please? Yeah, it is a normalizing factor, exactly as it happens in the Fourier transform. That's correct. So you take Sj and Sl, they are orthogonal. They are mutually orthogonal sets if J not equal to L. So the corresponding irreducible representations are inequal. You're taking a parliament of irreducible. So if J is not equal to L, the corresponding representations are irreducible. And each Sj is orthogonal linearly independent. So the sum of the elements is less than or equal to dimension of Ls, and dimension of Ls is mod G. But number of elements in Sj is dj squared. So the theorem follows. Yeah. So earlier I said it forms an orthonormal basis. No, we have not proved that yet. It's just an orthonormal linearly independent set. Okay. That's what I made a slip of tongue. So we get this inequality. We get this very, very important inequality that the sum of the squares of the degrees of the representation is bounded above by mod. We are going to show that actually equality appears here in 2.10. This particular the second inequality is actually an inequality. Already we know this for the symmetric group S3, the dihedral group of order 10, and the cyclic groups. We know this equality must hold for these three examples. So irreducible characters. Now, if phi from G to GLV is an irreducible representation, trace phi which is a class function, is called an irreducible character, and I'm going to denote it by chi sub phi. If phi is a one-dimensional, then chi sub phi is the same as phi as functions, and we make no distinction between phi and chi phi. If phi and psi are equivalent representations, then the characters are the same. Okay, and also chi phi g will be chi phi of x inverse gx for x g in g, because it is just it is just in an inner automorphism, and so when I apply the phi to it, it will be phi x inverse phi g phi x, and so all the matrices are conjugated by a fixed matrix, so you got equivalent representations. Similar matrices have the same trace, so the trace will be same. So chi phi is a class function. So now we get the first orthogonality relation. Suppose phi and psi are two irreducible representations of a finite group, and if they're equivalent, then the corresponding characters, the inner product is 1. If they're inequivalent, then the inner product of the characters is 0. Let's calculate. Direct calculation. Chi phi, chi psi. This is a normalizing factor. Then you just take chi phi g, chi psi g bar, and then it is, and then you put the definition of chi phi. It is a trace. It is a trace, and so it is phi I g psi j j g bar. and then what happens? It's mod G inverse summation. Just switch the two summations, and then now you see that we get an inner product inside. But recall from the theorem that we proved that phi I and psi jj is going to be 0 for all ij if they are inequivalent, right? And so this inner product is going to be 0 if the representations are inequivalent. On the other hand, if the representations are equivalent, we could take phi to be the same as psi because the character is the same for both. Equivalent representations are the same character, so we might as well take them to be equal. And then this simply reads phi I phi jj. Phi I phi jj by the previous theorem that we proved is 1 upon n delta ij. So that the characters chi phi and chi phi is 1 as we need. Any questions, please? This was a stepping stone. The previous theorem was a stepping stone to the first orthogonality relation, right? Any questions, please? All right. So we have proved the very important orthogonality. Let us draw some corollaries. If B is a family of characters for a parliament of irreducibles, then B is linearly independent. Of course, B is the character. If you take a parliament of irreducibles, if you take a parliament of irreducibles and take their characters, I'm going to get an orthonormal system, and an orthonormal system is automatically linearly independent. So there's nothing new, nothing unexpected. But the fact that this linearly independent family is a subset of class functions, and so now the class functions is going to be denoted by ZLG is going to be denoted the set of all class functions. So which means that dimension of Z of LG, it's very clear that dimension of Z of LG must be the number of conjugacy classes. Because I told you, how do I get a basis for the class functions? Take the conjugacy classes C1, C2, C3, blah, blah, blah. The function which is 1 on C1, 0 elsewhere. Function which is 1 on C2, 0 elsewhere, etc. That will give you a basis for the family of class functions. So the family of class functions is a vector space whose dimension is exactly the number of conjugacy classes. So we immediately get that the number of irreducible representations, the number of elements in a parliament of irreducible representations is less than or equal to the number of conjugacy classes. We want to prove that equality holds. Already we got an inequality. In fact, we see that the parliament of irreducibles, the cardinality is upper bounded by the number of conjugacy classes. Already we got the first important result. We got that if you take irreducible representations and you take their characters are orthonormal, and the number of elements and the number of such characters is upper bounded by the number of conjugacy classes. So let V be a vector space and M be a natural number. Then the V direct sum, V, M copies will be denoted by MV. Many books will denote it by V to the power M. And I'm going to denote it by MV because it's much easier to write down. If M equal to 0, we simply take MV to be 0. So multiplicity. So now let phi1, phi2, phi k be a parliament of irreducibles and rho be any representations. Then I know that this representation can be written as a direct sum of irreducible representations, right? And I can take them to be equivalent to each piece is going to be equivalent to one of these because I have a parliament of irreducibles. So the rho is equivalent to some direct sum of m1 copies of phi1, m2 copies of phi2, mk copies of phi k. Mj is called the multiplicity of rho, phi j in rho. And one can think of 2.11 as the Fourier decomposition. Okay, Fourier decomposition of, it's not It's not Fourier decomposition. It's a Fourier decomposition of rho. It's a Fourier decomposition of rho. I should make this change. I should cut this 2.11 and make it rho. Now take the trace of both. So take the trace. Take the trace and we get the character of rho is m1 times the character of phi1 plus da 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 plus mk times the character of phi. Now evaluate both sides at g equal to 1. Evaluate both sides at g equal to 1. We say the degree of g must be m1 times the degree of g1 plus da 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 plus mk times the degree of gk. We shall see later that this decomposition 2.12 prime is unique, and the number m1, m2, mk are called the multiplicities of the constituents phi1, phi2, pk in rho. So now with the notations above, the numbers mi in 2.11 are given by, mi is given by inner product rho with chi phi I. Well, and also the inner product of chi phi I and chi phi, inner product of chi rho and chi rho is m1 square plus da 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 plus mk square. This is called the Parseval formula. And now it follows from this that the decomposition is unique. The decomposition 2.11 is now unique. Okay, so take the inner product of 2.12 prime. Where is 2.12 prime? Take the inner product of this with chi of phi j. We get at once 2.13. Take the inner product. We have an orthogonality, of characters. Take the inner product. It's like a Fourier expansion, and you're extracting the coefficients, and so that follows at once. Next, if rho is equivalent to m1 phi1 plus m2 phi2 plus mk phi k, it is also equivalent to m1 prime phi1 plus m2 prime phi2 plus da 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 mk prime phi k. Then what happens? We get that chi rho is m1 times chi phi1 plus da da da, m1 prime chi phi1 plus da da da. Now orthogonality will give you mj equal to mj prime, and the proof is complete. And we have proved that the decomposition is unique. A representation rho of a finite group is irreducible if and only if this character chi rho is a unit vector. Two representations are equivalent if and only if they have the same character. 2.14 follows at once from the Parseval formula. Is this clear? 2.11 follows at once from the Parseval formula. In one direction, the result follows from 2.9, the next one, for the next one. Again, for the last part, if rho is m1 phi1 plus da 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 mk phi k, psi is m1 prime phi1 plus da 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 mk prime phi k. And if you know that chi rho equal to chi psi, then what happens? Then take the character of both sides. It means that m1 chi phi1 plus da 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 mk chi phi k equal to m1 prime chi phi1 plus da 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 mk prime chi phi k. Now use the uniqueness of Fourier expansion, or take inner product of both sides with chi phi1, and you get m1 equal to m1 prime, etc. Now to prove other important things such as sigma dj squared equal to the order of the group. Okay, that is k is the number of irreducible representations equal to the number of conjugacy classes. We need a few more tools that we now gather, such as the regular representation. Okay, so we have the notion of a regular representation. So what is a regular representation? The regular representation, basically, you need to recall the Cayley's theorem. So you know that a group of order n, can be realized as a subgroup of Sn. How do you do that? Take a group of order n. Take G1, G2, Gn. Take an element of the group, say Gj, and multiply. G1, Gj, G2, Gj, da da da, Gn, Gj. It is a permutation of the original ones. Correct? And so take this the Gj with which you multiplied. So you just map it to the permutation. And that's a isomorphism into. So the group has been realized as a group of permutations. So you know that every group of order n can be realized as a subgroup of Sn. And on Sn we have the standard representation. And that standard representation on Sn. So, okay, let me repeat. Take a group G of order n, let it sit inside Sn. Okay, and Sn can be realized as a group of permutation matrices. Okay, so we have got a representation of degree n. All these matrices we know have a common eigenvector with eigenvalue 1, and so this representation is irreducible, and it has CV as a constituent, the trivial representation. Now, we are going to see that every member of a parliament of irreducible representations appears in the decomposition. Again, I repeat, G has order n. G by Cayley's theorem can be realized as a subgroup of Sn, and Sn itself can be realized as a group of matrices, n cross n matrices, permutation matrices. How many permutation matrices are there? N factorial. That many. The group had n elements, but you realized it as a subgroup of Sn, and Sn is a group of n factorial permutation matrices. So our group G has a degree n representation, and this representation is called the standard representation of Sn. I've taken the standard representation of Sn, and the standard representation of the ambient Sn is called the regular representation of G. Clear? And this representation, all the permutation matrices have 1, 1, 1, 1, 1 as a common eigenvector, and the eigenvalue is always 1. Correct? And so this representation certainly breaks off into a it is not the representation that we got is not irreducible. I've given you a G invariant subspace, one dimensional G invariant subspace. That's a constituent. That's a constituent in the decomposition. But that constituent will correspond to the trivial representation. Now, G will have several elements in the parliament of irreducibles. Say it has got a degree 2 representation. It may have a degree 3 representation, for example. It may have a degree J DJ, degree DJ. It will appear this degree DJ representation in the parliament of irreducibles will appear as a constituent in the regular representation. The regular representation is not irreducible; it will decompose. But one of the from the parliament of irreducibles, every member will appear as a constituent. How many times will it appear as a constituent? What is the multiplicity? It will again be decay. It will be so the degree 3 representation will appear 3 times. So it will be d. So d plus d. So if the degree j representation, it will appear j times, dj times, dj times, not j times. I made a mistake. Is this clear, Shrav? Is it clear, Krishna?
Yes, sir.
So now, what are the Parseval formula? So what are we going to get? We are going to get each. So we are going to get the sum of the squares, no? When you take the trace, the regular representation. Call the regular representation rho. What is the degree of the regular representation? Please tell me. What is the dimensionality of it? Okay, let me repeat. G has order n. Where is it? Where is G sitting? Where have I embedded G into? Come on,
Sn.
Sn. And what am I doing? What is the and what did I do? I took the standard representation of Sn. No? And so, what is the degree of the representation?
N.
N. Or N is the order of G. So the degree of this degree of the regular representation is order of G. Correct? Point number one. So what is, and now if I take the trace, take the identity element and take the trace. What will the trace? What will be row of 1? Row of 1 with the identity matrix of size n, size mod G. No? So if I take the trace at G equal to 1, I'm going to get mod G. I'm going to get mod G. And then if you have a degree D representation, it is going to appear D times. So if you got a degree, so if you got an irreducible representation of degree D, if you got an irreducible representation phi of degree D, it's going to appear as phi direct sum, phi direct sum, phi direct sum, da da da, D times. But what will be the trace of phi? Trace of phi will be D. So it will be D plus D plus D, D times D squared. So you're going to get D1 squared plus D2 squared plus da 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 plus DK squared equal to G mod G. Okay. Yes. That magic formula we got.
Yes, sir.
So now we want to prove. So what is the basic thing we have to show? We have to show that if you take the regular representation, then in that regular representation, every irreducible represent a copy of every irreducible representation will appear as a constituent, and the multiplicity will be equal to the degree of the representation. That is the major thing. It's not difficult to prove. Remarkably, it is not difficult to prove at all. This theorem. This theorem is pretty easy to prove. Okay, and once we and all that we have to do is we need to set up the correct. We need to look at the problem correctly. For that, we need to introduce the group ring. What is the group ring? That's the next item. Okay, the group ring. The group algebra, or the group ring as they call it, some people, is that CG is the group algebra. What is the group algebra? For every element, or let me say it very simply, somewhat informally, you simply take the group elements G1, G2, G3, G4, da da da, Gn. You take the vector space generated by them. You simply take them as a basis. G1, G2, G3, da da da, Gn. You take them as basis. So lambda C1 G1 plus C2 G2 plus da 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 plus Cn Gn, where C1, C2, Cn are complex numbers. A little more formally, it is a vector space V. It is a vector space V. It is a vector space V over the complex numbers whose basis is Vg. I'm just being very, I'm just being very fussy in trying to distinguish the group element from the vector from the vector Vg. But for all practical purposes, I can just take G itself as an element of the vector space. And how do I do them? And now I'm going to make, so that's obviously a vector space. It's a vector space generated by the elements of the group, or for each element of the group you declare a symbol Vg, and the vector space generated by these symbols is a vector space. But I'm going to make it a ring. I'm going to make it a ring by defining a product. Vg, Vh is simply V of GH, and I demand that this product distributes over addition, that this multiplication distributes over addition, and this makes CG into a ring, and this ring contains a copy of C, right? This ring contains a copy of C because there is an element 1, right? In the group element, the identity element 1, and the corresponding element will be V1, and so the linear span of V1 will be basically C. So this ring called the group ring or the group algebra contains a copy of the complex numbers. The important This important entity called the group algebra was introduced by Frobenius, and so it is sometimes known as the Frobenius algebra. Now, as we go along, we will realize that what they have accomplished is marvelous. The accomplishment of Dedekind and Frobenius is really, really marvelous. And we need to go back 125 years where very little technology, mathematical technology, was available to those people. And how they could come up with this kind of a marvelous theory from bare hands is really it's just amazing. It's mind-boggling when you really think about it. So the idea of Dedekind was to take the group determinant and to factorize the group determinant. We will see later. First, do it for a circulant matrix: x1, x2, x3, x2, x3, x1, x3, x1, x2. What is the determinant of this? Add the three rows, you will realize that x1 plus x2 plus x3 is a factor. Add to the first row omega times the second row plus omega squared times the third row, and then see what you get. X1 plus omega x2 plus omega squared x3 will be a factor. So the circulant matrix factors into a product of three linear factors. And the circulant is exactly the group determinant for the cyclic group of order 3. And they can do the same thing for cyclic group of order n. It's a remarkable fact that for any abelian group, the group determinant factors into linear factors. When Dedekind did it for the symmetric group, he realized that the symmetric group factors, the group determinant factors into two linear factors. x1 plus x2 plus da plus xn will always be a factor of the group determinant. And then corresponding to the sign of the permutation, we got another linear factor. So he called this linear factors capital Phi1, capital Phi2. Then there is the group determinant is 6 by 6 determinant. So there should be another factor. The other factor should be a quartic. But this quartic factor is a square of a quadratic factor. Phi1, Phi2, Phi3 squared, where Phi3 is an irreducible quadratic factor. This factorization exactly corresponds to the three irreducible representations of S3. The trivial representation of degree 1, the sign representation of degree 1, and the geometrical representation of degree 2. And the geometrical representation of degree 2 will appear how many times? 2 times. Because what is the regular representation? The regular representation S3 is a group of order 6. It will be, the regular representation will be a degree 6 representation. How many times will the trivial representation appear? Once. How many times will the sign representation appear? Once. How many times will the degree 2 representation appears? 2. 1 plus 1 plus 2 plus 2. Phi1, Phi2, Phi3 squared. It's amazing. It couldn't be a coincidence. It's too marvelous to be a coincidence. Dedekind's idea was, he did it for the quaternion group also. For the quaternion group, you will get, the quaternion group has center as 1 comma minus 1. So G mod Z, Z is a normal subgroup, the center is a normal subgroup. G mod Z, the cyclic group of order 4. And so we got G quotient G mod Z. How many characters are there? It's a G mod Z is an abelian group. How many group homomorphisms are there from G mod Z to C star? 4. The dual group is 4. And so composing, you will get 4, you get 4 degree 1 representations. So D1, D2, D3, D4, they are all 1, 1, 1, 1, 4. How many elements are there in the quaternion group? 8. So 8 will be D1 squared plus D2 squared plus D3 squared plus D4 squared plus D5 squared. D5, there is a degree 2 representation. And how many times will the degree 2 representation appear? Twice, right? Multiplicity has to be 2 in the regular representation. So when Dedekind did the group, factorize the group determinant, he got 4 linear factors. Surprise, surprise, 1 quadratic factor squared. And what was this quadratic factor? This quadratic factor looked like the following: x1 minus x2 squared plus x1 minus x3 squared, like that. Sum of 4 squares. Immediately, sum of 4 squares doesn't factorize over the complex numbers, but it will factorize over the quaternions. Correct? So the idea is to extend the algebra to a larger algebra. So they called it hyper-complex systems. Quaternion, the algebra of quaternions is an associative algebra. It's not commutative. But never mind, let it not be commutative, let it be associative. So he was looking for a hyper-complex system. He was looking for an algebra in which this irreducible factor will factorize into linear factors. And we will see later that for the symmetric group S3, that algebra happens to be, it can be realized as a subalgebra of that algebra turns out to be the matrix algebra. So that's a degree 2 representation. So it's really, really amazing. So we'll continue this next time, because if I keep going, I cannot convert it to MP4. I'll stop recording.